Hello and welcome everyone to this next video that we have over here. This is Flexural member sample problem. So we're going to apply the formulas that we had discussed in our first video. If you haven't watched that video, please go over to our channel and search for the title Steel Design Part 1 for Flexural members, because the formulas that you will find there will be the ones that we will use as we go over a sample problem for this video. Okay, so let's go ahead and have a look at the problem that we are going to solve. So we can see here in our problem, this is a layout of a floor for beams and girders in a particular level of a structure. So we have the labels here for the end of our beams, and the points that we're going to analyze are also described here in our problem. So S is 3 meters, the one here on the right. So this is the spacing of the beams that you can see. So that's S, 3 meters. L is equal to 9 meters. So this would represent the length that we have labeled here as well. So that is the span of the beams that we have. Okay, so superimposed dead load is 6 kilopascal. Live load is 4.8 kilopascal. And we have the properties of beam CG. So we're going to analyze beam CG over here. The question here also has to do with beam CG. Okay, so we have the depth of that section. We have the flange width, the flange thickness, the thickness of the web, the section modulus, the RT, the weight of the beam, and Fy, the yield strength of steel, which is 345 megapascal. The question is, what is the maximum bending stress in beam CG? So that's what we're going to solve. First question in this problem. By the way, this is a problem. Situation problem. So we have 3 questions we're going to solve in this particular set of given values. All right, let's go ahead and have a look at the solution that we have prepared for this. Okay, so I'll be going through each step of the way. So before that, I just included here also the given that is provided in our problem. So basically, these are the same things that we saw in the previous slide. Now the question for the first part is the bending stress, no? The bending stress of beam CG. Okay. If you can still recall the bending stress, the formula for this is FB, that's equal to M multiplied by C distance divided by IX. So IX because our beams are loaded in such a way that there would be bending in the major axis of the beam. Okay, so MC over IX, that's the very basic formula. Well, if there is no IX, we just consider that we could actually rearrange the variables we have here in our problem or in our formula so that it becomes M over IX over C. This IX over C in the denominator is actually what? The section modulus of our beam. So we can actually express our bending stress in the form M over Sx, or the moment divided by the section modulus. This Sx is a value that is given here in our problem. It's a property of the section. So it's 2340 times 10 cubed mm cubed. Okay, so we need M, or the moment, acting on our beam CG. So since we want to have the FB maximum, then that means we should also get the maximum possible moment in our beam. Well, the maximum moment formula that we're going to apply, by the way, for this particular problem, if it is not clearly stated what type of support that we consider for the beam, we can safely assume that it's a simply supported beam. It's a simple beam. So for simply supported beams with a uniform distributed load all throughout, this is our formula for the maximum moment. It's WL squared over 8. Are you familiar with this? So simply supported beam, maximum moment formula. So the L here represents the span of our beam, which is 9 meters. We have it here. L is equal to 9 meters. So I will scroll down and I will now have here the solution that we are going to have. to determine W. Okay, so let's have our solution for W here, guys. So W is the total distributed load. How are we going to get this? So I'm going to show here the solution, and then I'll express why I will explain why I am doing it like this. So this would be SDL plus LLL times S times the weight of the beam times G. All right. So this G here is actually 9.81 meter per second squared, which is our gravitational acceleration. Okay. So what am I doing it like this? What is SDL plus LL? By the way, this is the superimposed dead load. The SDL, LL here refers to the live load, and S here refers to the tributary width. What do I mean by that? If we go back to the figure over here, we're analyzing beam CG. What is the tributary area of beam CG? That's the shaded red portion that we have here. So this is our tributary area, this red portion over here. What is its tributary width? The width, because the area, rectangular area, has a length and has a width. Okay? So this is rectangular. The length is, of course, the span L. What is the width? The width is this length over here. CG is at the middle, so its tributary width is 1/2 of the spacing to the next or the adjacent beam. So this would be S over 2 over here. All right. And it also has S over 2 to the left side or to the other side towards beam BF. So all in all, the tributary width is S over 2 plus S over 2. That would be a total of S. All right. So that is why here we just get the sum of these two different loads that we have multiplied by the tributary width to give us the distributed load in kilonewton per meter. Okay, so WB times G, this is the weight of the beam, that's 97 kilogram per meter. And G here is 9.81 meters per second squared. Okay, so if I'm going to get now the value of this, I will allow MathCAD to make the computations. Let me just rewrite this. All right, so this would be W equal to, this would be 33.352 kilonewton per meter. Okay, so that's our W. So we're now going to solve for our maximum moment. So this will be now W times L squared divided by 8. So our maximum moment for the beam will now be 337.685 kilonewton meter. Okay, so with this, we're now ready to solve for our maximum bending stress. So as what I have shown earlier, formula for this is M maximum over Sx, and our maximum bending stress for the beam is 144.31 megapascal. So let me just shade this to show that this is now our answer for part 1. Okay, so that's 144.31, the bending stress of beam CG. Okay. All right. So let's now go over to our next question. So this is now part 2 of our solution for this situation. So we have here, what is the permissible flexural stress if the compression flange of the beam is laterally supported at every 3 meters? Okay. So it is also said here that the CB that we are going to use is equal to 1. Okay, CB, if you could just watch that first video that I mentioned earlier, we have shown there that CB is actually a moment gradient multiplier. All right, that it has its own value, and there are specific instances or situations where we could just consider CB to be equal to 1. Okay, in this case, since it is clearly mentioned that we're going to use CB equals 1, so there's no need for us to evaluate under what condition this falls. So as long as it's mentioned in the problem to use CB equals 1, we just apply that right away. Okay? Okay, so how do we proceed about solving this problem? So what we're going to do here, as presented in our first video, is to check for the shape classification. We're going to check for the shape classification. So how do we do this? So first, let's start with the flanges. This is how we check for flanges. We are going to determine the width to thickness ratio of our flange. So this is 10. And we're going to check the limit. All right, the limit for the width to thickness ratio for it to be considered as a compact section. And that limit is 170 over square root of Fy. Okay. Now here in MathCat, I will just divide this by megapascal because I would want it to solve, to perform the calculation without the unit, because Fy here has a unit of megapascal. So if I'm not going to add this megapascal, look what happens. The units here get messed up. So I'm just going to add in a megapascal over here so that this would show the value for our limit. So it's 9.152. So what you notice here, our BF over 2TF is now greater than 170, okay, square over the square root of Fy. This is now our situation. That means the flange is non-compact because it has exceeded the limit for compact classification. Now, what about the web? Let's now consider the web. For the web, our limit or our width to thickness ratio is D over TW. Once again, these two values are given, no, in our introduction part. So we have there defined the depth, no, it's 350 mm, and also have TW here. In terms of mm, that would be 12 mm. Now we have a limit. For the flange width to thickness ratio, the limit is 1680 over the square root of Fy. And also add in this unit over here so that I will perform the calculation without the limit. And we have 90.448. Okay, so I'm going to copy this, have it pasted over here. And this would be less than 1680 over square root of Fy. So you notice 29.167, 90.448. All right, so what happens if our limit is less than the limit for compact? Well, we can say that the web is compact. All right. So we have these two classifications. Flange is non-compact, web is compact. Well, as long as one of these would cause the section to be classified as non-compact, then the section could generally be classified as non-compact. Okay? So in this case, our flange is non-compact, so we can now analyze or consider the section as a non-compact section. Okay? So we have determined that. What's our next step? All right. So our next step is compare LB and LC. Okay, so what is LB? Our LB here, okay, is the unbraced or laterally unsupported length over the beam. No? It's the laterally unsupported or unbraced length of the beam. Now, how are we going to determine our LB based on what we have here in our problem? So we can read the problem once again and look for phrases or keywords that would help us identify the laterally unbraced length, our LB. So according to the question, it says here that the compression flange of the beam is laterally supported at every 3 meters. This tells us what we are going to consider for our LB. It says that it's laterally supported at 3 meters. Therefore, our LB is 3 meters. All right? And mm, of course, that's 3,000 mm. Okay? So that would be for our LB. Now, what about our LC? So how do we determine our LC? Now, this is what I'm going to do. I'm going to get the minimum of two mentioned formulas in our code or in the ASD manual 9th edition by the AISC. And these are the two formulas. First formula is 200 BF over the square root of Fy. Okay, this is the first. Once again, I'm just adding the megapascal over here in the denominator so that I will cancel out the units. I would like to have the entire thing expressed in millimeters. And the next is 137,900 divided by D times Fy over, we have Bf times Tf. And once again, just to eliminate that unit for Fy, I'm going to add megapascal over here. This will now give us our LC. All right. Now, what do I do next? I noticed here the comparison between LB and LC, and I can see that LB is less than LC. Okay? LB is less than LC, and I have a flange that is non-compact. So if you are going to review the principle that we will apply for this, okay, the allowable bending stress formula that we are going to apply will now look like this. It's FB, Fy multiplied by 0.79 minus 0.000762 Bf over 2Tf multiplied by the square root of Fy. Alright. So this is our allowable bending stress. Okay? So it's 0.79 minus 0.000762 Bf over 2Tf square root of Fy. Once again, the megapascal to eliminate that unit. Okay? So this is our condition. LB less than LC. Flange is non-compact. We're going to apply this. Now, once again, for the different criteria on how we do this, please go over and watch that video that we had. You can take some screenshots for your personal notes that later on, when we look at the problems or when you watch this video, once again, you can refer to that. The step-by-step way on how we apply those formulas or interpret those formulas as mentioned in our structural book. All right. Now, let's go over and try to answer now the third question here in our problem. Okay. So, we have here, what is the permissible flexural stress if the compression flange of the beam is laterally supported only at the midspan? Okay, let's have a look at our solution over here. All right, so it's part 3. All right. So part 3, we're going to solve for allowable bending stress if LB is equal to L over 2. All right. So it says here, the beam is laterally supported only at the midspan. So our total length of the beam is 9 meters. Now there is a support at the middle. So the unbraced length would be 1/2. 1/2 of the total length. So that would be LB equals L over 2 or 4.5 meters. Okay. Now, we already solved for the value of LC earlier. That's 3.876. Okay. 3.76 meters or 3876 mm. So what do we see here? All right. What we could see here is that LB is greater than LC. No? LB is greater than LC. Now, what do we do, guys? What do we do if LB is greater than LC? Well, we have other criteria or other things to compare. All right. So the first value or quantity that we would want to know is the ratio of LB over RT. So this is 90. RT is a property of the section that was provided earlier. So that's 50 mm. So LB over RT is 90. And we would like to compare this with the square root of 703,270 CB divided by FY. So I'll just remove the unit for FY here. So it's 45.149. The other limit is square root of 3516,330 CB over FY over megapascal. So the other limit is 100.957. So if we're going to make our comparison, the comparison would look like this. Look at the values. L over RT is 90. First limit is 45. Upper limit is 100. So it looks like this. Less than L over RT. Okay. And then less than the upper limit square root of 3516,330. So we fall under this condition. If you're going to check that first video that we discussed, what happens if we fall under this specific condition? What we're going to do is we're going to solve for FB1, and then we're going to solve for FB3, and we're going to compare it with 0.6 of FY. All right. Okay. So this is what we're going to do. First, we're going to solve for FB1. So what is the formula for FB1? Formula is Fy multiplied by the quantity. This is a fairly long formula, but you can always refer to that first video that we have, or you could refer to your notes over there if you're able to take down notes. This is 2/3 minus, we have here in the numerator LB over RT squared times Fy divided by 10.55 times 10 raised to the 6 multiplied by CB. So it's a very long formula. Okay, let me just remove the unit once again so that I will have our FB1, which is 138.616 megapascal. Okay, that would be for our first. Okay, that's our first FB1. Now, first allowable bending stress that we're going to consider. All right, so let's now have our next one. So that's FB3. So our FB3 will have the formula 82740. So this would be CB divided by LB times D over AF, or BF times TF. So everything here, let's just express in terms of megapascal. Okay, and this would be our answer. So it's 340.416 megapascal. Okay. All right. 340 times 340.416 megapascal. Okay. So we now have our FB1, FB3, and the limit of these two that we're going to consider. How are we going to interpret? How are we going to choose? So the thing here is the instruction according to the code, we get the larger of these two. Larger of the two. Okay? So actually the FB is, first we get the larger of FB1 and FB3. Okay? But it should not exceed this one. It should not exceed 0.6 FY. Okay? So basically it looks like this. So the larger of the two, but it should not exceed 0.6 FY. Okay? So first, get the larger of the two, get the maximum of the two, and then compare it with 0.6 FY. Now, so it should not exceed 0.6 FY. So in this case, the larger is 340, but it should not exceed 207. Therefore, what prevails as our allowable bending stress is 207 megapascal. All right, so this will now be our answer for the problem. So it's 207 megapascal. Okay, so this will now be our answer for the third question. So our second question earlier, The answer was 223.72. Let me just have this highlighted. Okay, following the formula here, according to the code. And for the first question, that was 144.31 megapascal. All right, so thank you so much, guys. Thank you so much for your time watching this video, and I hope you learned something out of our sample problem to apply the principles and the code provisions that were discussed in our first video. So if you haven't watched that video, I really recommend that you have to watch it because it illustrates and also explains the different formulas that are provided for us. And feel free to comment down in this video down below if you have any questions relating to our discussion. Thank you so much, and till the next time.